Morning. Thanks a lot, everyone, for coming here on this wonderful Monday. It is my pleasure today to introduce Srini Iyer. Srini has spent several years now as a graduate student at University of Washington, working with Luke Zettelmoyer and Alvin Chung. Over these several years, he contributed a lot to the field of semantic parsing, generating code from natural language, generating natural language to code, combinations of the two, and the general progress in natural language processing and understanding. I think it's going to be a super exciting talk. I won't take much time from Srini, so without further ado, please welcome.
Thanks, Alex. Okay. Okay. Hi, everyone. I'm Srini, and I'm a graduate student at the University of Washington in Liz, right across the bridge. And I'm really excited to be talking here. So my talk today is going to be about learning to map natural language to general-purpose source code. I'm going to discuss new tasks, ways to obtain training resources, and also neural models to solve these tasks. Yeah, feel free to interrupt me at any point in the talk if you have questions. We have lots of time. Okay, so at a high level, the task that we want to solve is we want to start with a user's intent in natural language, and we want to train models that produce source code to do what the user wants. And the source code, we aim for the source code to be in a general-purpose programming language like Java or Python. So the user could be a developer who's writing a class to implement a vector, and the user may want to add a scalar to the vector in place, or the user could have just loaded some data and wants to plot the data as a scatter plot. And we want to be able to generate source code to do these things. Okay. The reason that we're aiming to generate general-purpose source code is the same programming language can be used for multiple domains and multiple applications. And also, these languages are highly expressive. So they have a very unrestricted structure and can be used to express various tasks. And thirdly, and this is probably the most important reason, and that is there exists a large programming community out there that's familiar with these languages, and that just makes it easy and inexpensive to obtain annotations for training models for these tasks, and for repeatedly improving our models over time and not letting them get stale. Okay. I want to now motivate the task of going from language to source code in terms of the kinds of applications that it enables. And if you look at these applications, we'll see that they're intended primarily for two main audiences, the developer and the non-expert user. So the developers would like models to help them automate writing code, and also models that help them double-check their work. And the non-expert user is someone who wants to be able to communicate with computers without having to learn to write code. Okay. So the first application that I had was building models that serve as a natural language assistant in programming IDEs. So you can imagine a developer having some partially written code, and then expresses some intent in natural language, and you can imagine having models that automatically produce this code for the developer in the IDE. And the result of this is it improves developer speed, but in addition to that, the code generated by our models can be more efficient and more readable than what the developer might normally write. Okay. So a second application of these models is to help developers check their code for efficiency or for consistency, or helping them locate bugs in their code. So as an example, let's say a developer is writing this Java class called violations, which has two member variables, including a list called violations. And then the developer wants to empty the violations list and goes ahead and writes this method to empty it, where the developer just assigns a new array list to this variable. And at this point, you can imagine Clippy popping up on the side here and saying something like, it looks like you're trying to empty a list. I might have a more efficient way to do this, and recommending the use of the clear method to achieve the same thing. Okay. The third application that I want to talk about is developers who want to know how to achieve a certain function X in a programming language Y. So as an example, here the developer wants to know how to use reflection to call a generic method in C#. So today, in order to achieve this, developers go to online forums like Stack Overflow, they post their question there, and someone has to look all through the internet and create an example that answers the question. But we can imagine training models that act as these Stack Overflow first responders that have access to the vast amount of coding information online, and that they can actually generate this example for developers. And once that's done, developers can take it and move it on to their programming IDEs. Okay. A more traditional example of mapping language to source code is the task of querying databases. So this task is mainly geared towards non-expert users, and so users typically ask a question in natural language, and to answer that, we usually have models that map this natural language utterance to a database query, and it's executed on the database, and results are presented back to the user. Okay. So along very similar lines, we can have non-expert users who have some data and would like to create certain visualizations from the data. And similarly, we can imagine having models that generate code in visualization packages like Seaborn here, and the code is then executed and results are presented to the user in the form of a chart. Okay, so if you look at all these examples, once again, we can see that some of them are aimed towards developers, some of them are aimed towards non-expert users. And models that we train for each of these audiences have a very different set of requirements. So for instance, for the developer, the source code that models generate is actually visible to them, and they can manipulate the source code. Whereas for the non-expert user, the code is latent, and they usually only see the output of execution of the code. So this means that for the developer, models that generate even partially correct code are also of use, because if the developers just have to change a few tokens and are still able to use the code, it's still worthwhile. Whereas for the non-expert user, the source code should be exactly correct because they don't actually see the source code. And what this also means is that for the non-expert user, it's very essential to have an explanation of the source code that has been executed by the model. And this is in order for them to be able to trust the results that they've been shown.
Is this where the user fully specifies what he needs, or is it a conversation where they fill in needed information?
Oh, it could be either of those scenarios. So I'm just speaking in general here.
Okay.
Right. And an explanation of the generated source code is also useful for the developer, but it more serves as a means of documentation of the source code. Okay. So the outline of my talk today is going to be focused on these two audiences. And so in the first part of my talk, I'm going to talk about models geared towards developers. And in the second part of my talk, I'm going to talk about models geared towards non-expert users. And finally, I'm going to conclude with some, I'm going to summarize everything we see and then conclude with some ideas for future research. So let me describe this a little bit more. So in the first part of my talk, it's going to be about contextual code generation for developers in programming IDEs. And I'm going to mainly talk about our two recent EMNLP papers. So our paper from last year, which introduces the task and introduces specialized models for contextual code generation, and our paper in EMNLP, which will be presented in November this year, which introduces programmatic idioms and how they can be used to scale up these language-to-code models. Okay, so most of the time in this talk is going to be spent on this first part. In the second part of the talk, which is geared towards non-expert users, we'll discuss some old work that I did in 2017. And this work is related to building natural language interfaces to databases and how we can do it for new database schemas in a way that's inexpensive and also in a way that results in models that are extensible and can be improved over time as we see more user interactions. Okay, and I'm going to spend relatively a smaller amount of time on this part. Okay, so that's my outline. So let's get started. Let's look at the task of contextual code generation for developers. Okay, so here's an example of some partially written code by a developer who's trying to implement a class that represents a weighted vector in Java. So the developer has defined two member variables, one called vec_elements to store elements of the vector, and another array called weights to store the weights. And we'll refer to this part as the programmatic context. Okay. So now the developer wants to add a scalar to this vector in place and expresses this intent as a Java doc. Right? And at this stage, we want models to automatically assist the developer by generating source code to do this. So this is the method that achieves this, and it accepts a scalar argument. It loops over the vec_elements array and adds this argument to every element of vec_elements. Okay. So I want to discuss some challenges that models that do generate this code have to face when they do this task. So the first challenge is the structure of this code depends on the type of vec_elements. If vec_elements were perhaps of a different type and not an array of double, the structure of this code could have been very different. So there's this explicit dependence on the context here. Secondly, models have to be able to associate the phrases in the natural language with elements in the context. So it has to understand that the word vector here refers to this array in the context, and not the weights array, even though they're both arrays of type double. Moving on, models also have to realize that when the natural language says add the scalar, it needs to accept a scalar argument in this method and then use that argument within this loop. And finally, models have to understand types. So models have to understand that vec_elements has a length property and is something that can be iterated over. Okay. All right. So let's move ahead. Let's say the developer has written this method now, and now wants to increment this vector. So at this point, the add method is now part of the context. So one way to write code for increment this vector is again to loop over all elements of vec_elements and add one to every element. But a neater way to do this is to call the add method with an argument of 1. And we can do this because the add method now exists in the context. So the point that I'm trying to make here is the structure of the code is heavily influenced by the presence or absence of elements in the context. Okay. So now that you have a brief idea of the task, let's look at how we can obtain training resources, and then we'll come back and make this task more crisp. Okay, so one way to obtain training data to train models for this task is to collect a lot of Java classes, and then hire annotators to label all the Java methods with natural language labels. And the problems with doing that is we require very highly skilled annotators, and that's going to really drive up costs in creating the data set. And also, we'd like to use natural language that has been written by the developers themselves and not by third-party programmers who looked at the class. So in order to get these two features from our data set, fortunately for us, there exists a large number of well-documented GitHub repositories that contain Java code. And in this work, we're going to try to use data directly from these repositories. So we start off with downloading 33,000 Java GitHub repositories. And the idea is to learn from inexpensive data from easily available on the web. So the first step that we do is we divide these repositories into our train, dev, and test sets. And we do this at this stage because we treat each repository as a domain of its own. And doing this will enable us to test the ability of the models that we train to generalize from one domain to the other at a later stage. Okay, all right. So this is an example Java file from one of the repositories. It comprises a class name, some variable declarations, and some method definitions that may or may not be prefixed with a Java doc. So the first thing that we do with these files is we remove any classes that derive from other classes in the same project, and we do that in order to keep our context simple and restricted to elements in the same file. We then pre-process the Java docs, we remove all the special tags, and in general, we perform a lot of steps to clean up the Java docs here. Okay. Now, this file contains two methods, add and inc. And for our code generation task, each of these methods will have an opportunity to be the target code that's generated. And when that happens, everything else in the file will be part of the environment. So this makes it more clear. So it's the same file shown twice. On the left-hand side, the add method is the target method. On the right-hand side, the inc method is the target method. And everything else shown in orange becomes the context. Okay? So let's look at the example on the left. And here, the add method is the target method that we want to generate using information from the context in orange. So we do some more pre-processing. And we replace the name of the method, so add with something generic like function name. And we also rename all the local variables and the function arguments canonically, starting at log0 and arg0. So we do this because this renaming does not affect the semantics of the method, and it'll just make it much easier to evaluate these methods later on when we train models. And
renaming does make it much easier to evaluate, but there is additional information in the names that the developer chose for the variables, situation and conditional. Mm-hmm. So do you use anything, do you have any way to recover this missing information that's actually something out there?
So the idea is to keep this information in all of the contextual elements, not take it out of the context. Mm-hmm. But this is it's only to take it off in the code that we are trying to, in the target code that we are trying to generate. So I was going to say that there's separate research by folks like Miltos, which does this task called extreme summarization, which takes in a method body and then outputs an informative method name. So methods like that could be used after the code is generated to actually recover method names and variable names. We could do a lot of, we could train many other models to recover the variable names as well. But for now, we're just going to do this. So after that, we pre-process the methods in the environment to strip the body and the parameters. And we do this to simplify the task to make the method declarations look like the variable declarations. And it'll just make our models simpler for now. OK, so now we're ready to make the task more crisp. So our task of contextual code generation is to generate a class method A conditioned on a natural language query Q, a list of variables and their types, TIVI, and a list of methods and their types, MIRI. Okay.
What's the intuition of using the code after the target as the context? Because in real time, you can imagine that you might not have access to something that somebody hasn't written as it. Right? It's coming after your target.
Yeah, that's a good question. So we're not assuming that the developers write these methods in any order.
But in this case, since it is actually using the function that was defined before.
Right. So in that case, the models could just learn to ignore those methods. But yeah, in a real life scenario, we'd only use everything that's already defined. So we do this on all of the files that we collect from GitHub, and we end up with millions of training examples. And just to make sure that our development cycle is fast and our models train in a reasonable amount of time, we use 100,000 examples for training and 2,000 examples for development and testing. And these are all from disjoint repositories. Okay. So I have some statistics of elements in our data set. On average, we have 5 variables in the environment. Our natural language is 13.7 words on average, and the source code is 26.3 tokens on average. And on average, we have 11 methods in the environment. Okay. All right, so that's the data set and the task. Let's now talk about models to do this task.
So on those methods at the bottom, like ink, do you give them the body of the method also, or just the declaration?
We only give the declaration. It will be, I mean, ideally, we'd want to give the body as well. We just, to make the task more tractable, we strip them off.
Do you also strip the comments from the methods?
Yes, we did. Yeah, we do have that information as part of the data set, but for this work, we did not use it. But I can imagine. So having all those components makes the encoder way more complicated. And I think a lot more work needs to be done to properly incorporate all these components. Okay, so in terms of models, a very strong candidate to do language to code tasks is the encoder-decoder model with attention. So we'll start off with this model, and then we'll make significant changes in all these components to perform well on our specific task. So our encoder, in our case, has to encode not only the natural language query, but also elements in the context. And the decoder is usually a sequential RNN that produces a sequence of code tokens. And the first change that we make is we modify this decoder to generate a sequence of parsing rules instead of code tokens. And these parsing rules define the syntax tree of the source code in a top-down, left-to-right fashion. And they can be put together to generate the syntax tree of the source code. Okay. Let's now zoom into each of these components and see in detail what changes we need to make. Okay, so the encoder needs to encode variables, methods, and the natural language query. The encoder has to create representations for all these elements, and we'd also like to have representations that are able to interact with each other later on in the model. So we use a uniform tokenization and embedding scheme for all these elements. So the way we tokenize these elements is if this is a type that needs to be encoded, we first separate all the special symbols. We then split based on underscores. We split based on camel casing. We lowercase all the elements. We apply byte pair encoding. And that's the final tokenization of every token that needs to be encoded. So we apply that to all these elements. And now let's see how do we encode each of these separately. So for variables, we have a type and a variable name. Each of them has their own subtokens. So we first embed all these elements. The pink boxes are the embeddings. We average these representations to give us ti and vi. We contextualize these using the BILSTM to give us ti hat and vi hat. And we will be attending over these representations later on in the decoder. Okay. And since our methods look exactly the same, so they have a return type and a method name, we do something very similar, and we end up with representations ri hat and mi hat. For the natural language query, we do something more traditional. So We split the natural language query into subtokens after byte pair encoding, and then we embed the tokens and then contextualize using BiLSTM to give us representations H1 to Hz. And we'll be attending over these representations in the decoder. Okay, so that's it for the encoder. Let's take a look at what happens in the decoder. So the backbone of the decoder is a sequence of LSTM cells, and each LSTM cell produces a distribution over parsing rules that define the syntax tree of the code that we're trying to generate. So for this example, on the top left, the first LSTM cell would produce member declaration, gives type or void, identifier NT, formal parameters, method body. The second LSTM cell would expand type or void. The third one would expand identifier NT. The fourth one would expand formal parameters.
So does that mean that you parse your target function and directly train it that way?
Yes. And yeah, these rules are from the, of course. Okay. So these rules are from the official Java grammar that's released by Antler. Okay, so let's zoom in at this stage and see what happens when the LSTM cell is expanding the formal parameters node. So as usual, the LSTM cell takes in the previous hidden state and outputs a new hidden state. But this transformation is dependent on 4 different inputs. So the first is an embedding of the current non-terminal that we're expanding, which is formal parameters here. The second input is an embedding of the previous production rule that was generated. The third input and the fourth input are an embedding of the parent production rule that produced this non-terminal and the LSTM state after the parent production rule was generated. And we do this in order to incorporate some awareness of the position of the rule in the larger syntax tree. So this makes the LSTM, the set of LSTM cells, not only a sequential model, but it also makes it a kind of tree structured model. And this gives us a new state ST, which we can use to attend on representations in the encoder. And let's look at how we do the attention mechanism. So our goal here is to attend not only on the natural language query, but also on the contextual elements. And we want to simulate a mechanism where the model first refers to the natural language query, selects important tokens, and based on that, selects elements from the context. And the idea is, because it's a contextual code generation task, we need to incorporate the target code is dependent on the context, and we may also need to copy elements from the context into the target code. Okay, so in order to incorporate this interaction, we perform a sequence of 2 back-to-back attentions, first on the natural language query, followed by then on the contextual elements. So we use ST to attend over the natural language query and get attention weights for each natural language token, and we compute a weighted sum based on these attention weights. We then use this weighted sum to attend over elements in the context. So this is all the variables, their types, the methods, and their types. And this gives us these weights beta, and then we compute a weighted sum using these beta weights. And finally, we use all these representations, we concat and project down, and this is what we're going to use to produce the final production rules. So additionally, I wanted to mention that because it's a contextual code generation task, a lot of elements in the code are from the context. So we use these attention weights here as a means to decide whether any of these contextual elements should be copied to the output target code or not. Okay. All right, so let's look at how the output is generated now. So we use CT to produce a distribution over output production rules, and we constrain this distribution to be only on rules that are valid right-hand sides of the left-hand side that we are trying to expand. So we're expanding formal parameters. So in the Antler grammar, these are the only target rules that are possible. So we choose one of these. Okay. And alternatively, we can also produce an identifier And the way we produce an identifier is we score all the identifiers as using a weighted sum of a generate probability and a copy probability. So this weight is computed using an activation function applied to the inner product of a learned vector B with our final context vector. And then as the probability of copying, we use the beta weights that we computed in the last slide in the attention mechanism. And the probability of generating is the probability of producing this particular rule. Okay. So that's it about the model. We train it in a supervised fashion by maximizing cross entropy on the Concode dataset. Before I move to baselines, I want to talk about what we do during decoding time. So when we have an example during test time that we are trying to decode, we run the encoder, and then we run the decoder using a stack. So we have a stack that stores all the non-terminals that need to be expanded together with LSTM states and pointers and any information needed to run the decoder. So at every step, a non-terminal is popped, decoder step is run, and all the new non-terminals that are generated on the right-hand side are pushed back onto the stack.
What kind of stack is it? Is it
I mean, we'd be putting it in the so that the leftmost non-terminal will be at the top. So
but it's not a neural stack. It's
right. It's a regular stack. Yeah. So the decoding will be done in this order. We also use a beam of stacks, and so in our work we use beam size of 5, and we have 5 separate predictions, and at the end we'll use the one that gives us the highest score. Right. Okay. So yeah.
Did I understand you right to say that you are hard imposing the grammatical restrictions on what can be generated, not having the machine learn the grammar in any way?
We are hard imposing that.
So the production rules are predefined by the Java grammar, right?
Yes.
How many production rules you use in your model?
So if you don't include the rules that generate identifiers, I believe there are 500 or so in the Antler grammar. And yeah, we cut off so we include a fixed number of rules that generate other identifiers. So there are a lot of identifiers that represent library methods and API, popular API calls, and those will need to be generated as part of the grammar in this model.
Okay, so those are pre-generated rules in the grammar.
Yeah, those will have to be learned from the training set. So I think the entire rule vocabulary might be, say, 20,000 rules, including those kinds of rules.
Okay. So if you said that you remove all the derived classes cases in your training data, right? So if the variables defining this class using some other classes, do you also remove these cases?
That could be. So I have an example where we have that problem. I'll show that. So we come up with some baseline models to compare a model with. The first model that we use is a retrieval model, where we retrieve the training an example from the training set, whose natural language is very similar to the natural language of the test example. And then we swap out the context of that example with the context of the test example. So we try to do as reasonable a job as we can by making sure that the types match and things like that. The next is the seek-to-seek baseline. So here the encoder and the decoder both operate on sequences of tokens. So the encoder encodes a concatenated version of the natural language and the contextual elements with appropriate separators, and the decoder decodes the source code one token at a time. And then next baseline is the seek to prod, which is the same as the seek to seek model, but we swap out the decoder with a grammar-based decoder, and we do this to assess the importance of grammar-based decoding for our task. Okay, so we make use of 2 main metrics to evaluate our models. So this exact match and blue score. And this kind of ties into the discussion that we had in the beginning about these models being used for developers and non-expert users. So the exact match would be a metric that we use for non-expert users, and the blue score is probably a metric that makes sense for developers.
Excuse me, this is blur 1 or blur 1 through 4, or?
It's the mean of all, so the regular corpus blue. The exact match is a very strict metric. Every token in the prediction has to match the corresponding token in the reference. And so our model gets a score of 12.5%, it's almost double that of seek to prod. And it just shows that all of these specific changes that we made in the components specific to our task has contributed to performance. And seek to prod itself gets almost double the performance of seek to seek, and it shows the importance of grammar-based decoding for this task. And all the models outperform retrieval. Okay. So in terms of blue score, blue is a metric borrowed from the MT community, and we use it here as a means of assigning partial credit to model outputs. So we get a blue score of 24.4. It is higher than all the rest of the models, but the delta is not as much as the exact match. And the reason for that would be that any model that is able to generate a reasonable enough method with parentheses in the right place, a return keyword in the right place, is already able to achieve a blue score of around 18. So all these changes build upon a much higher baseline. But we'll see later on in this talk how we can push up these blue numbers to a much higher value. Okay. We did some feature ablations on our development set. So we start off with an accuracy of 9.8%, and if we remove our contextual elements, such variables and methods, we suffer a large hit in accuracy, primarily because this is a contextual code generation task. If we remove the interaction between our attention mechanisms and replace it by a single regular attention, it also results in a performance hit. And finally, if we do not do source code specific tokenization, that also affects performance. So all of these are important for these kinds of models. So before I move on to the next section, I want to present some model outputs from our model at this stage. So let's see, here is an example where the natural language gets the value of the tags property. And in the environment, there is a variable called tags, which is of type list of string. So our model correctly learns to return the tags property. It uses the correct return type as a return type of the method, and it throws in this extra null check here. Okay. So the second example that I had is where the natural language says convert mixed case to underscores. And here there's a method called add underscores in the environment. And so the model learns to accept a string argument, pass it to the add underscores method, and return a string argument, which is the return type of this method. So it kind of learns to use methods in the environment. So this is the example I showed in the beginning with Clippy. So this is an actual output from our model. The natural language says empty the violations list, and the reference, unfortunately, is assigning a new variable of this type to violations, and the prediction just says use clear. And this is a way where we can improve the code that's already written by developers or suggest changes in real time. The last example I had is where the natural language says creates and adds a new limit. And there's a variable called limits of type list in the environment. So in this case, both the prediction and the reference are very similar. So they both create a new element, they add it to the limits list, and they return the variable. The only difference is in the type of the element that's created. And the reference wants to create a variable of type limit. But if you look at the input, this type never actually occurs. So models can probably infer this type by looking at other files in the same folder or other types that are defined elsewhere. But in the way we formulated the task, this is not accessible. So the model just decides to copy this element type here instead. And anyway, I show this as an example of a case where even though a few tokens are wrong, this piece of code could still be useful to developers. Okay, so I now want to move to talk about programmatic idioms as a way to scale up these models to larger data sets. So this is work that we're going to present in the upcoming EMNLP. And work along very similar lines has also been happening in MSR by Alex and Richard. And so here I'll talk about the way we did it in our paper. Okay. So So one problem with syntax-aware decoding is when it's used for with real-world programming grammars, the decoder ends up having to perform a large number of steps even to generate a small snippet of code. So in this example, this is a if-then-else subtree of a larger syntax tree, and it takes our decoder 11 decoding rules to generate this when we use the Antler grammar. And this is a very popular snippet of code that's used over and over again. So so what we wanted to do was we wanted to augment the decoder to generate this entire structure in one step instead of going through these series of steps. Okay, so this can, the idea was this can significantly improve training time, and it can also improve alignments between language phrases in the input and code snippets in the output. So so based on definitions by Miltos and others in 2014, we call these frequently occurring subtrees of syntax trees, we call them code idioms. So this slide kind of shows an example of the kind of improvements in alignments that I was talking about. So in this example that we've been looking at, if we generate based on idioms, models may be able to learn associations between phrases like vector in place and this loop, or phrases like adds a scalar and this function body that accepts a scalar, or this increment statement inside the loop. This is just a hypothesis. We're hoping that it can learn alignments like this. Okay, so in the remainder of this section, I'll talk about how we can identify what these idioms are, and then how we can apply them during decoding in our models. Okay, so we want to identify the top K idioms from our training corpus, and the way we've defined idioms, this directly translates to finding the top K most frequent subtrees from our training corpus, from the syntax trees of our training corpus. And the number of subtrees are really large to enumerate, so we make use of a simple trick where we observe that if S prime is a subtree of S, it's just as frequently occurring as S, or even more. So, so this would mean that the most frequently occurring subtree that's non-trivial is a subtree of depth 2, and that's the method that we use. So we repeatedly identify these depth 2 subtrees. We add them to our idioms list, and we post-process our training set to replace them with single rules. And this is very similar to the BPE algorithm, which is used for identifying most frequently occurring subsequences by merging frequently occurring character bigrams. So I have an example of this. Let's say this if statement here is the depth 2 subtree that's most frequent in our data set. So we first identify it by enumerating all the depth 2 subtrees, and then we collapse this subtree by taking the leaf nodes and putting it into the parent, and this would be our first idiomatic rule. Then we post-process all of the training set to replace all occurrences of this depth 2 subtree with this depth 1 subtree, and we just repeat this process to get more and more idioms, and that's how we get the top K idioms from our training corpus. Okay. So here's another example. Let's say this is the next most frequent subtree. And if you observe here, this is the idiom that we extracted in the previous step. So again, we collapsed this to become a depth 1 subtree, but this is now a depth 3 idiom because it was built on top of an idiom that we already extracted before. Okay, so let's discuss how can we apply these idioms during decoding. So our idea is to take these idioms and add them as new grammar rules in the grammar that the decoder uses. And once we do that, we'll train the decoder to produce the shortest parse for the training syntax trees with these rules added to the grammar. And the way we implement it is we get syntax trees from the training set, we apply as many idioms as we can, and we compress the tree until it cannot be compressed further, and then we'll train the decoder on these compressed trees. So this is an algorithmic version of exactly what I said before. So we get the syntax tree of every training example, and we continue to apply all the idioms in the order that we extracted them until we cannot compress the tree anymore. So as an example, if this is an example syntax tree in our training set, we can see that there are two spots where we can apply the first idiom that we extracted. And so we apply them, and it gives us this compressed tree. And then there's an opportunity to apply the second idiom that we extracted. So we apply that, and it gives us this compressed tree. And finally, we train our decoder to generate this tree. Okay, so we apply this method on the Concode dataset using the same model that we discussed before. So we get the top 200 idioms, and we augment the decoder with these idioms. So as soon as we do that, our blue score improves by 2.2% to 26.6, and the exact match score remains about the same, but we also managed to cut down the training time from 27 hours to 13 hours. Okay, so then the question arises: how do these two variables, so the blue score and the training time, vary with the number of idioms that we choose? So that's what we try to figure out next. So we vary the number of idioms that we add, and then we plot training time and blue score. So if we look at training time, it drastically reduces when we add the first few hundred idioms, and it continues to reduce and kind of plateaus down at the right-hand side of this chart. And we suspect that this happens because the idioms that are extracted at this stage are really large and very specific to the training set. And since we build our development and test sets from totally different domains, those idioms do not contribute to a lot of compression anymore. If you look at blue score, the trend is slightly similar. So it rises when we add a couple of hundred idioms, stays fairly constant, and then drops here when we include 600 idioms. And again, we think that the idioms that we add here are very specialized, and it now gives the models an avenue to overfit to these idioms. Okay. So now we take advantage of this reduced training time, and so we left aside a lot of training data in the beginning of the talk when we built the data set. So we add some of the training data back inside, and we're able to train it faster because of using idioms. So we pick 400 idioms, and we train the same model on 2x, 3x, and 5x the amount of data. And this helps us improve our exact match from 12 to 13.4, and our blue score from 26.6 to 28.9. Okay. So we've seen how we can use idioms as a means to make decoding faster, improve alignments probably, and scale up these models to larger data sets. So before I end this section, I want to show some examples of the kind of idioms that we extracted because they're highly interpretable. So here's an idiom for creating a new object. The name of the object and the name of the constructor and the arguments are going to be decoded later on, but this is an idiom that's used pretty often. Another idiom is a try-catch block. The blocks can be decoded later on, but this general structure is pretty common. So the two idioms on this slide are an integer-based for loop and a very popular method in Java for outputting to the console, that's system.out.println, Normally, these would take 13 to 14 steps to generate, but we've extracted these as really useful idioms to produce in one step. And finally, here is a compound idiom, and this is a combination of an if-then idiom, a try-catch idiom, and a new object creation idiom. And this is an idiom that will be extracted at a later step in the extraction process because it's a large idiom. Okay. All right, so that was it for the first part of my talk, geared towards developers. I'm going to switch gears a little bit now and talk about a task that's geared towards non-expert users. And in this part of the talk, we're going to discuss how we can build a natural language interface to a database. We're going to see how we can do this for new database schemas in an inexpensive way, and also move away from models that are only trained once and move to a paradigm where we can continue to improve our models over time as we see more user utterances. And we'll see that the key to doing this is to use a general purpose programming language that many programmers are familiar with, which makes getting annotations cheap. So we're going to use a 3-step strategy. So first, we're going to use a popular database query language that a large number of programmers are familiar with. Then we are going to have to train models to map natural language to this popular language. And finally, we need to put all this together to build a mechanism to get user feedback, and also a mechanism to use this feedback and get new annotations to improve our models. So I'm going to quickly describe parts 1 and 2 and spend maybe a little more time on part 3. So this slide makes things more crisp. And so traditionally, the way natural language interfaces to databases have been built is users ask a query in natural language, and that has been mapped by a semantic parser to a meaning representation in a language like lambda calculus. And this has been deterministically converted to SQL using handwritten rules, and that has been executed, and results are presented back to the user. So the main complaint with this kind of workflow is that it's really expensive to obtain annotations for logical forms. The annotators so this kind of a workflow is only accessible to folks in the research community, and is not a general approach that can be deployed by anyone. And also because the annotations are so expensive to obtain, the model is usually just trained once, and it's never improved later on because of the annotation cost. So keeping with our theme in this talk of using general purpose programming languages, so we propose that let's try and train models that map natural language directly to SQL. And so the deep learning models that we train these days should be powerful enough to do this mapping. And the idea is that the fraction of programmers that understand SQL is way, way larger than programmers that understand the logical form representation that's always been used. So we're going to replace this pipeline with a model that maps natural language directly to SQL. Okay, but the obvious question that comes up is this even possible? How well can we map natural language to SQL? So we explored this in our ACL 2017 paper, and we showed that simple sequence-to-sequence models that do data augmentation with a paraphrasing component are able to very effectively map language to SQL. And we showed that for commonly used semantic parsing tasks of mapping language to meaning representations, these language to SQL models approach accuracies that are fairly close to accuracies that the past models have achieved. So this chart shows denotational accuracies for some semantic parsing datasets. Okay, and since we showed this in 2017, various more sophisticated models and resources for mapping natural language to SQL have come out from various other groups, including WikiSQL from Salesforce and Spider from folks at Yale. Okay. So as a follow-up, we also showed neural models in NACL 2018 that map natural language to SQL in a multi-turn scenario by conditioning on code that was generated in previous turns. And that has also led to an additional line of language to SQL research. And this year, again, the Spark dataset was released from the group at Yale to study multi-turn language to SQL. So in 2017, when we did this, we used simple encoder-decoder models with attention, fitted with this paraphrasing component that does data augmentation by creating variations of the natural language in the training set. And the motivation for doing that was we found that when there are these online databases that are queried by hundreds of users, users usually have only a couple of hundred SQL queries that they want to get answers to, but they just have numerous ways to express the same intent, which is what makes the task challenging. So this kind of a model worked out pretty well, and of course there are way more sophisticated models now that also generalize across domains. Okay, so we've seen parts 1 and 2. Now let's look at how we can put all this together and build a natural language interface for a new domain. So the workflow that we suggested in 2017 was this. So we'd first train a model on synthetically generated data. And as part of the paper, we put out a set of language to SQL templates that are fairly general and can be used for any database schema that has reasonably named schema elements. And these would be simple queries like selecting from a single table or just joining two tables and using approximate template-based natural language utterances. So we train this model on the synthetic data and we deploy it and let users interact with this model. And the model would provide users with results and an explanation of the generated code. So users would then give feedback as to whether it's correct or wrong, and wrongly marked utterances would be sent to a SQL programmer that we hire from the crowd, and we'd collect these annotations, and every now and then we'd retrain this model. And we expected that the model would improve in performance and be able to answer most of the users' questions after a few iterations of this. So we actually set about to try this out by building a natural language interface for the semantic scholar database at AI2. So this is a database of academic papers built by AI2, and we want to see if we can build a natural language interface for this. Okay, so we conducted this three-stage experiment, and in each stage we recruited 10 different users, and we asked them to put 10 questions each to our model. The model is initially trained on synthetic data, and the model would provide results and an explanation. So these were grad students recruited from our university who regularly use online resources to query for papers, authors, venues, etc. Okay, so I want to talk about the kind of explanation that we provided back to the users. So we built a user interface for them to query this database, and we also gave them two kinds of assists for them to be able to trust the output of our model or not. The first assist was type highlighting. So if the query was papers by Michael Jordan in ICRA in 2016, we'd actually take the output of our entity linking module and annotate the input utterance with the types of all the entities, as this is what will be input to our semantic parsing model, and it helps the user understand whether the model correctly identified the right types or not. And if these are wrong, the user can go ahead and mark that the output is wrong. The second assist was utterance paraphrasing. So what we did here was, of course, the generated SQL query is not presented to the user, but we would search in our training set to see if there was a query that exactly matched what we generated after we abstract over any constants and strings. And if we found an exact match, we would take the natural language associated with that query in the training set and substitute the entities and present that to the user. So in this example, there was an exact match for the query that our model generated for this in our training set, and the natural language associated with that was what papers does X have in Y in Z, and then we put in the entities from the user's query. So by paraphrasing it with something that already exists in the training set, we're able to help the user be more confident that the result is correct. So using these two assists, we asked the user for feedback, and wrongly annotated questions were sent to a crowd worker from Upwork, who also had access to the database, so could run the queries and make sure that they're correct. And we'd collect these annotations and retrain the model at the end of every stage. So we did this for 3 stages, and this is this chart shows the results that we came up with. So the model started with an accuracy of 25%. This is purely template-based, and it rose to 64% at the end of 3 stages. And this is model accuracy as computed by the number of queries that the users marked as correct. And simultaneously, the amount of annotation required by the programmer that we hire also significantly reduces. And we expected both of these trends to continue for a few more stages, and then we expected to have a model that is able to correctly answer most of the questions that most users have, and only miss a small long tail of complex questions that new users might come up with. So okay, so in summary, we're able to use popular database query language to get these natural language interfaces running for online systems in an inexpensive way, and in a way that allows the model to improve in quality over time. And okay, so that was the second part of my talk. I'm now going to quickly summarize everything we saw and discuss some ideas for future research. Okay, I introduced the task of mapping natural language to general purpose source code, and then we saw the importance of context and how it heavily influences the structure of the target code. We saw how we can modify encoder-decoder attention models to train this model to improve performance specific to our task. And then we saw how we can use code idioms to scale up our models to larger data sets. And we saw 2 main ways of obtaining supervision to train these models. The first is from large-scale corpora available on the web, and the second is through a combination of user feedback and using the expertise of programmers available on the crowd. Okay, all right. So looking ahead, if you look at the semantic parsing datasets that we had even 5 years ago, they only had a few thousand examples. And recently, in the last few years, we've managed to scale up the sizes of these datasets to several hundreds of thousands of examples. And in this talk, we scaled up our model to 500,000 examples. However, there are still tens of millions of unused examples on GitHub. And one area for future research is how can we train faster and more distributed models that are able to leverage a much larger quantity of data that's available online. So one area for future research might be to look at attention-only based models that are able to decode syntactically correct code and are able to do this in a faster and more distributed way. A second area for future work is whether we can use this data to create pre-trained representations for elements on the source code side. So can we get pre-trained representations for code idioms? Can we get pre-trained representations for popular APIs that we can reuse in downstream tasks and not have to learn over and over again? Thirdly, in this talk, we modified our decoder to generate syntactically correct code, but the decoder can still get away with various things like not declaring variables before using them, ignoring function parameters, and things like that. Another thing is the decoder is not familiar with various programming invariants, like the order of predicates in a conjunctive clause does not matter, or the order of certain statements does not matter. So determining what is the most general way to incorporate these constraints in decoders without resorting to programming language specific hard coding is an important area for future work. Okay, so next I want to talk about explaining predictions back to users. And this is really important because it's a means to improve trust between the user and the model. So this is particularly important for non-expert users, as we see in this example here, where the user wants to see all papers from PLDI 2014, and the model happens to ignore 2014. And when the model presents results to the user, it's going to be particularly hard for the user to catch this error. And to avoid that, we need a model with high accuracy that's able to explain what the code actually does back to the user. So we studied this to some extent in a context-independent fashion in our 2016 paper, but extending these models to function in a more context-aware and interaction-aware fashion is an important area for future work. Okay, so next I want to talk about models that learn from background knowledge. And so every day for different programming languages, various new APIs are being released, new packages are being released, and it takes a significant amount of time for these APIs to get enough adoption and start appearing in online corpora, because only when that happens will the usage of those APIs trickle into the models that we train, at least right now. So fortunately, these new APIs usually are accompanied with a very detailed set of documentation, and training models that can understand this documentation and start to use these methods in code that's synthesized just by learning from the documentation is an important area for future work. So I have an example of the Boto API that helps people access AWS services from Python here. And I think, I looked into this API, which helps users delete all the data that the device has stored about them. And it comes with a few paragraphs of natural language descriptions, some example usage, and a description of all the parameters. So models that are trained to understand this documentation and use them in generated code have to resolve at least two main challenges. So the first is the style of the natural language in documentation is very different from the style that users use to query the models, and models would need to map one style to the other and learn associations between them in order to succeed at this task. And also, both the natural language, this is the natural language in the documentation, and the natural language used by users are usually at different levels of abstractions. The documentation is usually more low-level and detailed, whereas users ask more high-level utterances. And again, models should be able to learn to associate these two levels of abstraction in order to succeed at this task. The last piece of future work that I wanted to talk about was related to interactive programming. So this is a paradigm where users alternate between natural language and code, and usually the future interactions are based on outputs of the past interactions. So we can imagine training models to assist users in to automatically generate any of these code cells, and it's a scenario where so this is an exploratory style of programming, usually used for machine learning and data science applications. And here the user and system function as a team to solve a particular task. And this is very popularly practiced today in the form of Jupyter notebooks, where these notebooks usually contain a title, some markdown in natural language, and then some code cells. And that goes on and on. So here is a Jupyter notebook where the user is training a decision tree classifier. So the user first loads features, splits the data set, and then trains the model here. So we can imagine it being extremely useful to users to have any of these code cells auto-generated, conditioned on all of the prior history in the notebook. So we explored this to some extent in a paper called Juice, which we'll present in the upcoming EMLP. Here we collect a large data set of 1.5 million Python notebooks together with a clean test set for evaluating. And the task is to generate these code cells conditioned on the entirety of the prior history. Okay. We've still barely scratched the surface of these kinds of tasks, and working on this area is really important for future work in this area. Okay, so that was the end of my talk. I want to thank all my collaborators. Luke Zettelmar and Alvin Chung are my advisors at UW. Luke is also a research manager at FAIR, and Alvin has now moved to Berkeley. I worked closely with Yannis Konstas while he was a postdoc at UW, and he's now a professor at Heraetvot in Edinburgh, and I've worked closely with Jayant when he was at AI2, and now he's part of Semantic Machines. So I've interned at AI2 and FAIR, and both of them have contributed to work I presented here. That's all. That's the end of my talk. I'll leave you with these funny code comments, and I'm happy to take any questions.
Questions?
Thanks for the talk.
Thanks.
Do you have any thoughts about explainability when it comes to more complex queries, like the new query showing up in a spider dataset for SQL, for example? They would be much harder to explain than the queries you showed up for semantic scholar.
Right. So so one idea is to make use of examples that we know are perfectly correct, and kind of establish some kind of mapping between the generated code and a code that we know is correct. So maybe models can reveal to the user that this source code is created mostly from these few examples in the training set, and actually show those examples to the user, where the user can see the examples and have more faith that the resulting code is correct. So we did something along similar lines for the experiment that we ran for generating the natural language interface. And over there we required an exact match. So we needed to be absolutely sure that it is exactly the same piece of code. But we could extend that to even multiple pieces of code in the training set, and maybe the user can see a pattern of how two pieces of code can be put together to generate the example. If you have, if you're not working with general purpose source code, but a specific meaning representation, I imagine the way it's done right now is there are handwritten rules that deterministically convert certain operations to natural language, and then we can work on kind of paraphrasing that kind of natural language to something that's more human-like.
I have a question about the evaluation part. I feel like it's a little bit not fit to the task. Obviously, that's what you guys have been using it for evaluating. But have you? There's this reward-based systems to train these agents, and you also talked about this interactive, like maybe episodic kind of learning or teaching an agent incrementally. So in that case, maybe reward-based. Like I'm just wondering if there are any work out there. Have you been thinking maybe it's a good research direction? I don't know.
So we've been thinking of that as a important research direction for the interactive programming paradigm for things like the Python notebook data set. So over there we have, actually in our test set, we have access to test cases and outputs and things like that. So definitely that would be a very natural approach to take in those kinds of data sets. In the ones that
like different kind of reward functions even, right?
Yes.
That would be specific to the task.
Yes, like how many test cases does it pass,
Yeah.
and things like that. For the task I presented here, I know that some people have suggested to me that another metric I could use is the edit distance, which makes sense for developers, and it measures how much they have to change the code to actually get to their goal. So that could be something that we could use in the future. And another metric that that people have looked at is to see only the sequence of API calls. So we assume that developers know how to write code. They just need help in the sequence of methods that they need to call. So just consider the method calls and do some kind of precision recall on them and compare those.
There's also the semantics, right? You had an example where emptying a vector
Yeah.
two different ways, and if the golden set is one and you only predict the other, and semantic the same,
Yes.
you can't use per score, I suppose.
Yeah. So at least on my data set, I think 2% of the cases were, I did a small manual evaluation, and 2% of the cases were such that we generated correct code, but the reference was something else. Yeah.
And maybe the evaluation could be in different direction, I suppose.
Absolutely. For the Java data set, I spent a lot of time trying to use these frameworks for writing unit tests like Ant and Maven. But that didn't really end well because after a whole bunch of filtering, using only repositories that use Maven and putting more constraints on them, I ended up with just very few repositories in the test set, just a few tens actually.
Making sure this thing's built is nice.
Yeah. So they have to build as well.
Yes.
Oh, there's also one more thing that I was just thinking. Has anyone, or have you ever thought of using online lectures where, teaching kids how to code?
Perfect. So the actually in this data set that we released, the test set is exactly that. So it's online assignments by professors in the form of notebooks. So they designate a code cell as, put your answer here, and it would come accompanied with test cases. So you can put your answer there and run it. And that's just
more. Maybe we'll talk after.
Yeah. That's just perfect.
Sort of working.
Yeah. So actually, I had a sorry.
Yeah, go ahead.
I had a question about. So in your introduction, you said that there are a lot of instances in Stack Overflow where people post solutions for stuff. So do you think your model could be adapted for more higher level completions, like say how to produce substrings of a string or something like that? So where it's not more granular but more higher level. And do you think that, I believe that there would be data out there for some things like these, and do you think your model would be as is good to be trained on those kinds of data?
Right. So that's a very important question. It's like the level of abstraction at which the natural language instruction resides, right? So, for example, in the Java data set, we're only looking at methods, and there is this unsaid rule for writing Java methods that the method should only have one function, and that kind of seals the level of abstraction at which we generate. But the Stack Overflow is obviously at a very different level of abstraction. So we want to kind of assign these high-level phrases as labels to these large pieces of code. So in none of these tasks are we actually trying to produce new pieces of code. The task is mostly about using existing code and swapping out the domain. So the hypothesis is a lot of code that we regularly use is already written, and we usually want to take it and adapt it to our own domain, and that's what models need to learn to do. So yes, I mean, actually in 2016 we have a task that takes in Stack Overflow style of natural language and ranks code based on that. But again, it would be a more reasonable thing to do to already have a code corpus and retrieve from that code corpus rather than having the model figure out that this phrase actually stands for this large chunk of code.
Yeah, maybe the models are still not that great at actually coming up with solutions for new problems. So if it's just going to retrieve something that's out there, then yeah, your retrieval method could be the best thing to do.
And another source of training these models that we talk about quite a lot is using training data from other programming languages to generate code for a new programming language, and kind of have rules to map lines of code from this language to that language, and then get an example from there and synthesize it here for this language.
Just curious if there's been any work. This is all kind of at the fuzzy level where don't have any guarantees or anything. At a lower level where the model is actually grounded in the results of a simulator or something, or a runtime, so that it can try out things and see the values and adjust its strategy accordingly, and then give back, if it has some notion of correctness, give back a trusted kind of answer.
So I believe all of the work in that area is related to when the input contains input-output examples, where the models try to get all the input-output examples correct. And I believe that's also been paired with natural language because sometimes there are many different programs that'll solve all the input-output cases, and the natural language helps the model be biased towards a certain program. But without input-output examples, I'm not sure if there's any work, at least not that I'm aware of.
For Stack Overflow, because I did some research on Stack Overflow on deep learning frameworks, but I found one major issue is that people often don't know which API to use or which parameter of that API to use. I think that's related to the feature you mentioned, related to the documentation parsing or something. I think it's like we can, because I think for your work it's basically a lot of the success depends on the context of that classifier, and in a Stack Overflow scenario, we have a very large context based on a lot of the standard library or specific libraries the user are using. I think this brings a new challenge here.
Absolutely. So I guess you're talking about the kind of zero-shot case where, so in Stack Overflow, a lot of questions can be answered by looking at code that's already online. But there are also these cases where users are just are not used to going and reading APIs, or they're just they're just lazy and want someone else to do it for them. But just models that can learn to consume documentation, and if they're even just able to tell the users that these are the APIs you need to use.
Yeah, and maybe more in a more user-friendly way of documentation, because actually a lot of documentation nobody wants to read it.
It's it can get very large.
Yeah. I have one more question for your first part of work. So do you have any kind of user studying the evaluation? Because typically it would be a difference between the natural language, because for the comments it's mostly written after you write the code, right?
The Java docs?
Java docs.
It could be either way. I've seen both. So the human evaluation was tricky, at least for our data set, because I tried to do a few, but the models here have a much larger advantage over me. They have access to huge training sets, tons and tons of prior examples, and I don't have access to those examples. So for me, it's just hard to read the language and come up with the code. But that does not mean that models are not able to do it. So in terms of, because of that problem, it's hard for us to put a number to how humans would do.
Yeah, because I feel like it's related to the interactive here. Because when I want to write a new method, the first the natural language description I come up with maybe very fuzzy. It's kind of not very clearly intended. But after maybe the model can give me the template, I can further integrate my previous natural language description with more details, so that the model can come up with a new, better method synthesize.
Yeah. This is what Alex and I were just discussing, just recently. So I was thinking we can use some kind of past GitHub commits to kind of figure out how the language and code involves, but that may or may not work. Depends on how frequently people are committing their code. We might be able to find a fraction of repositories that are helpful for that.
Jupyter history might be more applicable than GitHub commits. Usually commit at a much broader granularity than...
Does Jupyter store the history?
It does quite often, yes.
Okay, that's going to be very useful.
Not in the distro, but...
Okay.
more frequently than you usually commit your code to the logical stages. Okay, any more questions? I think we are basically out of time. Okay, thank you, Srini.
Thanks.